All right. Good evening, everyone. Thanks for joining today's session. Thank you, Avinash and Krishna Kumar, for joining. This will be week 12. This will be related to week 12 lectures. That is your final week of this course. And today we will be solving few problems related to heat exchangers. And probably you could expect a similar kind of questions in your exams. Okay. And we will have one more lecture, not a lecture. We will have one more problem solving session where we will be revising the entire course. So that will be tomorrow, same time, 7 to 9 p.m. Otherwise, we will be discussing only heat exchangers today. Okay. So we will quickly go through what has been taught in the heat exchanger topic, and then we will solve a problem, and then floor will be open for you guys to ask any questions that we left previously. Okay. um, and regarding the um questions on week 8 and week 9 that I think Avinash and Mustafa came up with, I contacted professor, and soon it will be resolved. However, the other question, there's a change in answer. So, for example, the what- so this question number 5, is actually the answers are right. Okay, and similarly, even week 8, the answers are right. I will explain you. And however, the pressure thing, that will be mostly rectified soon. Okay, so that is wrong. We will discuss this more at the end of today's lecture. Okay, so probably Mustafa also might join. So we will discuss this at the end of today's lecture. So we will go through the heat exchangers first, and we will come back to that later. Okay, so those are a couple of announcements, and now yeah, we will go through the topics. So this week, we all know. Let me check my recordings. Okay, yeah. So this week, uh, we touched about on heat exchangers. We basically saw two kinds of methods. One is LMTD, and the other one is epsilon NTU method, right? Uh, uh, Basically, that was the main topic that we covered. So initially we started with two kinds of heat exchangers that are available in any industry. uh, uh, in any process industry, you will see a direct contact heat exchangers also, and indirect contact heat exchangers. In this course, we mostly dealt with indirect contact heat exchangers. We didn't study about cooling towers or uh, other heat exchangers of direct contact. Okay, so we will stick to indirect contact heat exchangers for this course. So what does it mean? So you have heat exchange is basically exchanging heat between a hot and cold fluid. We want to either cool uh, our fluid of interest, or we need to heat up the fluid of interest, and that we are going to do it with another fluid which is of higher temperatures. Okay, so for example, you will have a tube flow. It's called shell and tube heat exchangers. You will have a shell, and inside the tube will be there, and in the tube, hot liquid will be flowing, and outside the shell, the cold fluid will be flowing, and in between them, there will be the tube will be there, and across which the heat just transfers. That's the main thing. And you can either have hot fluid or cold fluid inside. It's based on the convenience. Okay, typically the tube flow is always hot. Sometimes the tube flow is also cold in places like boilers. Okay. uh, yeah, so basically you can either have a parallel flow heat exchanger where uh, both the hot and cold fluid flows along in the same direction, and in the counterflow heat exchanger where it flows in the opposite direction. And this is how the temperature profiles look along the length of the heat exchanger. And if it's a boiling and condensation, during boiling or condensation, temperature is not going to change, so you will have a straight line for the fluid which is going to undergo, which is undergoing phase change. And for that fluid, you can take the C to be infinite, because during that time temperature doesn't change. Okay. And similarly, same goes with the boiling. Now, then we discuss something called overall heat transfer coefficients. So this is basically the same, the resistance network that we draw, and then we will, find the total resistance, right? So from total resistance, you can get back what we call overall heat transfer coefficient. So basically, in this case, heat exchanger is our areas of interest. So you will have a hot fluid and you will have a cold fluid going, you know, on either side of this tube. So you will have convective heat transfer at the inner portion or inner side of the tube, conductive heat transfer across the tube thickness, and there will be another convective heat transfer on the cold side of the tube, right? So that if you draw a resistance network, and you can write the resistance like this. And uh, if we define heat to be some overall heat transfer coefficient, some coefficient U times reference area times the temperature difference across this. So from hot fluid to cold fluid, then how can you express? So then you can relate these two relations, and then you can end up having an expression for overall heat transfer coefficient U. Okay, it can either, the reference area can either be outer surface area or it can be inner surface area. And if the velocities are very low, then you can ignore kind of conductive resistance, you can ignore, but it's general, people add it, it's not a big deal. And there is something called fouling factor, that is this is because for in industrial practice, what people do is, because of a lot of time, uh, you know uh, the the duration along the duration of operation of heat exchanger, as time goes, uh, it becomes dirty, basically, because of the flow going inside it. The fluid will have some impurities that settles in the inner portion or outer portion of the tube, and corrosion can happen. All these could add resistance to your flow, and to quantify that resistance, people usually give it as a fouling factor. And if you know the clean overall heat transfer coefficient, based on the fouling factor, you can find the dirty overall heat transfer coefficient. And basically, this is an additional resistance that that adds in the inner and the outer layer of the tube. Okay, so this is an additional reason, because of the settlement of these impurities and the uh, oxidization of these tube materials, it can happen, then rust formation, all these things could add additional resistance. That is what we are adding it as a two separate resistance here. So this will be for a dirty tube, uh, and the difference between this and this will be the fouling factor. Okay. And then we went on analyzing how to find the heat transfer. So heat transfer for this kind of heat exchanger, total heat transfer, when a liquid flows from a hot side to cold, when the liquid is cooled down from a higher temperature to lower temperature, what is the total heat transfer? We can express it as m dot c. And same goes with the cold fluid, it is also undergoing same temperature range change. Now, if you want to, let's say for a given, if you want, so in general practice, we want temperature of the hot fluid to reduce to a certain value. So we usually know what is the heat transfer I require from this heat exchanger. Now, if that is the case, then I have to design the heat exchanger. So designing the heat exchanger, basically the design parameter here is the total area required for the heat exchanger. So in this case, the U is basically from the operating conditions. If you change the velocity, your heat transfer coefficient is going to change. So for a given U, and Cp you do not have more control because it's a material property, and m dot is something industry provides. So this is the m dot, I'm so this is a fluid which is coming from different process. So this is the m dot rate at which this fluid is coming. I want to cool it down. So these, if you fix these, then I want to design a heat exchanger in such a way that I cool it down to a certain temperature. So if that is the case, what is the amount of area I require? So that is kind of a design problem. What is the amount of heat exchange area I require? So to do that, um, we uh, we basically derived this relation. So for initially we started with parallel flow arrangement. So this is the temperature profile along the length. Now we want to write Q in terms of overall heat transfer coefficient and the area. Okay, so here Q is not in terms of area, it is in terms of mass flow rate, but we want area. So for that we need to we can write it in terms of overall heat transfer coefficient and the delta T. So now in a parallel flow heat exchanger or even in counter flow, your temperature profile is going to keep on change along the length. So usually till now we have always said that inside it is some temperature, outside fluid is at some temperature, so we didn't vary the temperature of the fluid. But here, as the fluid is flowing, the temperatures are changing, so the temperature differences are changing. So we need to find some mean temperature. For that we did this analysis. Basically we took an elemental strip along this, and then we did the energy balance, and that energy balance is something like this, and we performed some mathematical rearrangements, and then we ended up having something like this. So this term actually is kind of like a temperature difference. It gives a kind of mean temperature difference, uh, which you can replace it for a varying temperature profiles. So along this, there are temperature profile is varying, but even if it is varying, you can if you use this as your temperature difference, then you will be able to get accurate solution. Okay, so this is called log mean temperature difference, or LMTD. Okay, kind of like a mean temperature difference. And similarly you can do for counterflow, but the solution is not going to change. It's like just that the terminal temperature difference. Based on terminal temperature difference, you can express your heat transfer rate, and from here you can find area basically. Okay, so remember this is a design problem, so which means you will know what is the exit, you will know what is inlet, and you will know at least one of the exit temperature. So only then you will be able to solve this problem. Okay, and then you will be finding area. Now in some places what we will know, so I have some heat exchanger, I want to quantify the performance of this heat exchanger, let's say. So I'm giving some m dot and I'm giving some temperature at the inlet, but I don't know what is the temperature at the outlet. So that is something that we need to find out. Okay, so given the heat exchanger, given its area, so we need to find out what is the temperature that is going to, how much this heat exchanger is going to cool down my hot fluid, or how much this heat exchanger is going to heat up the cold fluid, right? So then it becomes like a for performance evaluation of the heat exchanger. Now we don't know both the temperatures at the exit. Okay, so then we follow some other method called NTU epsilon method, and for that you can also use LMTD, but you need to do some iterations to find out you to uh, narrow it down to a certain value. Okay, so instead you can use NTU epsilon method, where NTU is nothing but number of transfer units and epsilon is the effectiveness here. Okay, here it's the effectiveness of heat exchanger, which is nothing but the actual heat transfer divided by the maximum heat transfer that can happen. Okay, so um, this maximum heat transfer is actually defined as C min, the minimum heat capacity, not the specific heat capacity, heat capacity. Heat capacity means m dot into C. Okay, minimum heat capacity times the uh, inlet temperatures of both hot and cold fluid. Okay, so and this Q max is never you cannot achieve in parallel flow heat exchanger at all. So you think about it, why you cannot achieve it. So if you look at this figure, you will be able to understand this. Now, however, in counterflow, if effectiveness can be one, and you can able to you will be able to achieve, but because of practical reasons, you won't be able to reach epsilon equal to 1. Okay, Um, Epsilon can also be expressed in terms of delta T of minimum capacity fluid by delta T max. Okay, and so then you perform certain uh, manipulations to the same equation. So there is no difference. It's Q is equal to delta A LMTD equation. Uh, but we go one step back. So here we took we took the this portion of this derivation, and then we started doing it a little bit differently. We introduced these things, and then we rearranged it so that you can express your heat transfer, or so that you can express effectiveness and NTU with some relation. Okay, so at the end, the NTU, if you define it as UA by C min, which is the number of transfer units, then your effectiveness formulation will become something like this for a parallel flow heat exchanger. Similarly, you can repeat this analysis for counterflow, and you will end up having an effectiveness of this. Okay, these are the two formulas that you may need to remember. And for parallel flow and counterflow, or you can derive it anytime. So if you know how to derive it, so basically you will be able to so for a given problem, let's say for a given heat exchanger, we know area, we know heat transfer coefficient, overall heat transfer coefficient. We also know m dot is also given, m dot C min. So basically NTU you will find. So once you find NTU, you substitute it here, C's are known, you will find effectiveness. So once you find effectiveness is Q actual by Q max. Q max is already known. So you can find the Q actual. So once you know Q actual, we know Q is m dot C delta T, right? For different fluids, for hot fluid it's m dot C delta T for hot, and m dot C delta T for cold. So this is going to be same. So for different fluids you will have same heat transfer, and then that from there you can find the exit temperatures of hot fluid and cold fluid, and from there also you can find the heat transfer. Okay, so this itself will directly give you the actual heat transfer. So basically to quantify the performance of this heat exchanger, so for that you need to use epsilon NTU. If it's a design problem, you need to use LMTD method. Okay, so that is the thing. And if it's a boiling or condensation, you will end up having the specific heat ratios to be something like this, and heat capacity ratios to be 0. And if the heat capacity ratio is 0, the effectiveness is simply 1 minus exponent of minus NTU. Okay. You can expect similar questions in your exams too. So that's why we will solve some. I have like 3 questions in this problem, so we will solve some 3 questions in this topic. Okay. If you have any questions, please let me know. If not, we will continue with the problems. Okay. I hope there are no questions. All right. We will solve the first problem. Okay. Um, so the first problem tells, I didn't mark it. So the first problem goes like this: a hot water stream of flow rate 1 kg per second is to be cooled from 95 to 60 degrees Celsius in a heat exchanger by contact with a large stream of cold water flowing at uh, 2 kilograms per second at an inlet temperature of 40 degrees Celsius. Now, you're asked to calculate heat transfer area needed for this configuration, and they have also given it's a counterflow arrangement. So basically, uh, probably I can draw a schematic so that you can understand. So you have Okay, so hot fluid is flowing, so probably I will draw the other way. I think it's fine. Yeah. So the hot fluid is flowing this side. Let's say it flows along the tube, and the cold fluid enters and leaves this way. So basically, it is a counterflow arrangement, right? So it will go in the opposite direction. Now, the hot fluid goes from 95 degrees Celsius to 60 degrees Celsius. This is, let's say, TH1 and TH2 hot. And similarly, the cold fluid goes from TC1 at 40 degrees Celsius to TC2. We don't know what is this TC2. And the m dot here is 1 kg per second, and the m dot here is 2 kg per second. Okay, now the CP is given. Okay, let's write down the CP. CP is 4.18 kilojoules per kg Kelvin, and this is CP of water, and you know both are water only, so you can take the same CPs. Okay, and overall heat transfer coefficient U is given, which is 100 watt per meter square Kelvin. So it has same units as convective heat transfer coefficient. I mean, basically, this is also a overall convective heat transfer coefficient. Okay, so we are supposed to find what is the heat transfer area required. What is the area required? So there are 4 options given. So first, we need to solve it to find it out. So to begin with, how do we begin? So we need to find the area. So for that, we know it's a from heat transfer only we will find area. Heat transfer is nothing but UA delta T LM, or LMTD, right? uh, there's a log mean temperature, and so it's a design problem, so we will use LMTD. So for that, for this we need to know what is the heat transfer Q. Q is nothing but m dot H CH TH1 minus TH2. This is the overall energy change for the hot fluid. Similarly, the overall energy change for the cold fluid is going to be m dot C2 minus m dot C1. So the 1 and 2 changes because it's this is a hot and this is cold, right? Cold fluid gets heated up, so 2 will be larger than 1. So we know hot fluid's terminal temperature, so we can use this. So hot fluid 1 kg per second and 4.18 kilojoules per kg Kelvin times TH1 is 95. From 95 it is getting cooled down to 96, 60. So it's going to be 95 minus 60. So this is going to be some value. How much is this coming out to be? So I'm getting something like 146.3 kilowatts. Okay. This is the total heat transfer happening in this heat exchanger. So this is not going to change. Now we know heat transfer. Now we also need to find delta TLM. So we know delta TLM to be delta T1 or delta T2, I guess, delta T2 minus delta T1 divided by logarithm of delta T2 by delta T1. So now it's a counterflow arrangement. If you go back to this thing, yeah. So this is your LMTD. So what T2 and T1 refers is the temperature difference at the two terminals, you can say. Okay. So maybe if I plot that, this is along the length, This is the length of the heat exchanger. So the hot fluid enters. Hot fluid enters at 90 degrees, 95 degrees Celsius, and it cools down to 60 degrees Celsius. 95 degree, 60 degree. This is TH2, TH1. And now cold fluid enters, but it's a counterflow arrangement. So cold fluid enters at what is it? 40 degrees Celsius, and it gets heated up. We don't know how much is this. So this is TC1, which is 40 degrees Celsius, to TC2. Okay. Now this delta T2 is nothing but this is 1, this is 2, right? Delta T2 is TH2 minus TC1, and delta T1 is TH1 minus TC2. So this is the basically the temperature difference at these two terminals is what we are using. Okay, TH2 minus TC1 and TH1 minus TC2. So temperature difference at the two terminals. So we can find this, but we don't know what is TC2. First, we should find that. We can use this heat transfer itself to find out. So we know m dot h ch th1 minus th2 is nothing but this is the total heat transfer. That is the same heat transfer that is heat that is going to the cold fluid, Tc2 minus Tc1. So this we found out to be 146.3 kilowatts, which is equal to, correct, m dot c is 2 kg per second. 2 times Cp is 4.18 into 10 power 3 times Tc2 minus Tc1 is 40 degrees Celsius. Okay, so can one of you quickly calculate and let me know what are these numbers? Tc2 will be 40 plus 146.3 divided by 2 into 4.18. How much is this coming out to be? So the temperature is like I'm getting 17.5. Please check my calculations. So I'm getting something like 57.5 degrees Celsius. So it is entering at 40, leaves at 57.5, higher temperature. Now you can find delta T2 and delta T1. TH2 minus TC1, which is 60 minus 40 is 20 degrees Celsius, and delta T1 is 95 minus 57.5, 95 minus 57.5, which will be 30 32.5, I guess. 95 minus 37.5, 37.5 degrees Celsius. Okay, so now you can find delta TLM or LMTD. So I write it delta TLM. How is professor writing? Okay, he didn't express this. It's just LMTD. Okay, we'll also follow LMTD. LMTD equal to T2 minus T1 divided by natural log of T2 by T1. So the numerator would be negative, the denominator also would be negative, because 20 by 37.5 is less than 1. So natural log of anything less than 1 is actually in the negative. So it's minus 0.628. 20 minus 375, 37.5. So a total will be in positive. Okay, 27.84 degree Celsius. So this side it's 20, this is 37.5. So let's say if you take a mean of this, what will happen? 28.7, something you can think about it. So so what I'm trying to do here is, you have temperature difference of this much here, you have temperature difference of this much, so we are finding some mean temperature. So let's say I find the mean temperature of these two temperature difference, then that corresponds to around mean of this is corresponds to the around 28.75 degrees Celsius. So this will actually be wrong, right? So certainly your LMTD is 1 degrees at least less than this to a mean temperature. And uh, you can see that this is a counterflow arrangement, so your error is less, just 1 degree Celsius. And if you calculate area or heat transfer based on this, it will not be up to the mark. Okay, but if it's a parallel flow heat exchanger, this error would be even larger, and you will overestimate your heat transfer rates, or underestimate your area of uh, heat exchanger. Okay, so just to give you an idea. Anyway, now this is the LMTD 27.84 degrees Celsius. Now you can substitute them in the Q is equal to UA LMTD. At the end we want to find area. So area is nothing but Q by U times LMTD. So Q is 146.3 kilowatts, so 10 power 3 divided by this is 1000 times LMTD is 27.84. Okay, so 10 power 3 and 1000 gets cancelled. You can write this as, so it should be like something like 6 or 5, I guess 6 meter cube, something like that. Oh, okay, yeah, so it's like 5.255 meter square. This is the total heat exchanger area you require. So I think it has an option. So this is your 5.26. You can write, you can round it off to 2 decimals. 5.26 meter cube. Okay. So this is how you perform a calculation for for design kind of problems. Similarly, you can do for parallel flow heat exchangers too, but we are not going to do it. We will. If you have any doubts, please let me know. I hope this is clear. The first problem. It's just straightforward calculation. And now the second problem. So if there are any doubt, please stop me in between. So the second problem is again a counterflow heat exchanger we are dealing with this time, but has a heat transfer area of 10 meter square and the overall heat transfer coefficient of 500 watt per meter square Kelvin. So it is used to cool 1.5 kilograms of oil, which is initially at this temperature, by 0.5 kilograms of stream of air with the inlet temperature of this much. Okay, so now we are asked to find what is the outlet temperature of both the streams and the total heat transfer rate. So basically we are asked to find out the performance of the heat exchanger. Now only the temperatures at the inlet of both oil and water is given. We do not know the temperatures at the exit. Okay, so here from the problem statement itself you can understand we should use something like uh, we, we should use epsilon NTU method. Okay, so it's again counterflow, so let me draw the temperature differences so that it will be more clear. This is along the length. So the hot fluid enters at 115 degrees Celsius and then cools down to some temperature. We don't know that. So this is TH1 is 115 degrees Celsius. cools down to TH2. And cold fluid enters at some other temperature, and it gets, sorry, I mean, it enters at 15 degrees Celsius. TC1 is 15 degrees Celsius, and it leaves at some higher temperature. We also need to find out that. So this is the counterflow arrangement. The other parameters are U is given, overall heat transfer coefficient 500 watt per meter square Kelvin, and area is given, area is 10 meter square, and what else is given? M dot H and M dot C is given. M dot H is 1.5 kilogram per second. This is oil, and the water is, M dot C is 0.5 kilograms per second. This is water. So we also need to know the CP. So CP values are, for oil it is, we can write as CH. For oil it is 2.25 into 10 power 3 joules per kg Kelvin, and for water it is 4.18 into 10 power 3 joules per kg Kelvin. Okay. So now we are supposed to find Q. What is Q? What is TH2? And what is TC2? All these things we need to find. Okay. So we know we have to use epsilon NTU method, but where do we start? um, So we initially have to start. So we know for a, in epsilon MTU method, for a counterflow heat exchanger or parallel flow heat exchanger, we have relation for epsilon and NTU. Okay, so we need to find NTU first, and we need to find specific heat ratios, and from there you can find epsilon. And once you find epsilon, heat transfer rates and temperatures you can find out. Okay, so from epsilon only you can find heat transfer rate, and epsilon is a function of NTU, number of transfer units. So you start with NTU, number of transfer units, which is nothing but UA by C min. You can write it as M dot C min, minimum heat capacity. Okay. How much is this? U and A are given. M dot C min we need to find out. This is 500 times 10 divided by M dot C min. So which one is minimum? Let's find out what is M dot HCH. M dot H is 1.5 into CH. CH is 2.25 into 10 power 3. And similarly M dot CCC is 0.5 times 4.18 into 10 power 3. So from just the numbers we can say it's going to be M dot CCC. So this is like 4.18 half, but here it's going to be 2.25 times 1.5, so it's going to be larger than this. But anyway, we'll calculate it once. 1.5 into 2.25 is 3.375 into 10 power 3. This is 4.18 by 2, which is 2.09 into 10 power 3. So this is M dot C min. So now you can find NTU. NTU is going to be 500 times 10 divided by 2.09 into 10 power 3. So you can sorry, so you can remove this. So 5 divided by 2 is like 2.5, 2.39, 2.3923. So this is your NTU, and the epsilon relation is 1 minus, I guess it's exponential of minus NTU times 1 minus C ratio. This is C ratio, maybe I will put it as C bar, divided by 1 minus C or exponential of minus NTU into 1 minus C. I guess this is right. Let's check. 1 minus exponential of minus NTU 1 minus C bar minus C bar. Okay, yeah. So this C bar, I think professor used just C to avoid confusion with CP, C, and then C ratios. I just took it as a C bar, nothing much. This is C min by C max. Okay. So this you can readily calculate. C bar, C min by C max is going to be 2.09 by, correct, right? C min by C max 2.09 by 3.375. 3.375 should be around 0.6. Yeah, so it's 0.6193. Now we know NTU, we know C bar, so you can directly find epsilon. Epsilon is 1 minus exponential of minus 2.3923 into 1 minus C is 1 minus, this thing, it's going to be 0.3807 divided by 1 minus 0.6193 times exponential of minus 2.3923 2.3807. So how much is this epsilon coming out to be? If you guys calculate, please let me know. 2.3923 this exponential is coming out to be 0.402218. Now multiply this with 6193 and then 1 minus 0.402184. Okay, so I'm not sure whether this is right answer, but this is what I'm getting. So 0.7961. Okay, this is epsilon and it should be less than 1. Okay, for counterflow heat exchanger it can go up to 1. That's it. So now epsilon is 0.7961. So what is effectiveness? This is nothing but Q actual heat transfer divided by Q maximum. What is the maximum heat transfer here? That's going to be simply when the hot fluid is, so it's a counterflow arrangement, right? The hot fluid enters at TH1, cold fluid enters at TC1. So at the exit of the heat exchanger, the hot fluid can reduce up to TC1, right? It cannot reduce below that because the cold fluid is entering at TC1. That is the temperature limit there. And similarly, the cold fluid can reach up to hot fluid temperature because that is the temperature it enters, hot fluid enters. So here the cold fluid has the C min. So this is nothing but Q actual times Q max is m dot C min times TH1 minus TC1. Okay. TH1 minus TC1. Now Q actual or Q is what we want to find out. So we can just write it as Q. Q is nothing but epsilon times m dot C min TH1 minus TC1. This is going to be equal to, effectiveness is 0.7961, m dot C min is 2.09 into 10 power 3 times TH1 is 115 degrees Celsius and TC1 is 15 degrees Celsius. Okay. Now you can find this to be, how much will this be? 0.7961 times 2.09. It's into 100. Okay. It's around 166.385 kilowatt. So this is your heat transfer rate. Okay. This is your total actual heat transfer rate in your heat exchanger. So now that you have known this, we know this heat transfer is going to be, this is what is going to change your temperature of both hot fluid and cold fluid. So you can write Q to be m dot HCH times TH1 minus TH2. Also you can write this to be m dot CCC times TC2 minus TC1. So here, from here you can get a TH2. That is going to be Q divided by m dot HCH yeah, sorry, TH1 minus Q divided by m dot HCH, and from here you can find TC2 to be TC1 plus Q divided by m dot CCC. Okay, so what is Q? Q is 166.384 divided by m dot HCH. We already found out, right? M dot HCH is 3.375. So divided by 3.375, it's 49.3. So 11 from 115 it is reduced by 49.3 degrees Celsius. So it's coming out to be something like 65.7 degree Celsius. Okay. And similarly here it's 166.385 divided by 2.09, which is 79.6 plus 15. This is coming out to be 94.6 degrees Celsius. So these are your answers, 65 and 94.6. So basically it goes up to 94.6 degrees Celsius, 65 degrees Celsius. Okay. Sorry, I think the other way. TH2 is 65.7 and TC2 is 94.6. So one observation here you can see is this TC2, okay, is higher than TH2. Okay, this can happen because it's a counterflow heat exchanger. Okay, but this cannot happen if it's a parallel flow heat exchanger. So you cannot have cold fluid getting heated up above hot fluid, more than hot fluid. In counterflow you will be able to have this All right. It's also, it has a lot of steps, but I think if you know how to calculate it, it should be straightforward. I hope this is also clear. If there are any questions, please let me know. So last question was also something like 160. All right. I hope there is no problems. It's a You can also try this condensation problem. I do not have here condensation or boiling problem, so you can check the uh, heat transfer book in Cropera and you can find out more problems like this. And if you find any difficulty in solving any of the problem, please let me know. You can either reach out by email or uh, there's one more session we will have tomorrow, so at that time you can come and ask. Okay. All right. Uh, One final problem we have here for today. So this you guys are going to answer me. So the third question is something like this: in a tube pass, in a tube pass means like one tube pass and one shell pass heat exchanger. Hot fluid enters at 310 degrees Celsius and leaves at 190 degrees Celsius. Okay. While the cold fluid enters at 50 degrees Celsius and leaves at 180 degrees Celsius. So which of the two arrangements, whether parallel flow or counter flow, will transfer more heat? So this is the question. So now you're supposed to select an answer from these options. So what do you guys think? So maybe I will draw a heat exchanger. Both parallel flow and counter flow I will draw. So in the meanwhile you can give your answers. You can either unmute yourself or you can use chat to give your answers. A, B, A is parallel flow, B is counter flow, C is both have equal heat transfer, D is none of the above. So this is parallel flow. So it's terminal 1, terminal 2, terminal 1, terminal 2. So the hot fluid enters at 310 degrees Celsius and leaves at 190 degrees Celsius. Three ten, 190. And the cold fluid enters at 50, leaves at 180. Leaves at 180. Okay. So if I want to draw something for counter flow, so it enters at 310 and leaves at 190, and it enters at 50 and leaves at 180. So this is 190, so it leaves at 180, so it's a little bit less than this. T 180. So what do you guys think? Which one will have highest heat transfer? Should we do some calculations to find out? So we can assume that m dot h is same and m dot c is same for both, both parallel flow and counter flow heat exchanger. So for a given m dot h and m dot c, and of course ch and cc, the heat transfer rate is nothing but m dot h ch into th1 minus th2, and or you can also write heat transfer to the m dot c cc, m dot c cc, tc2 minus tc1. Okay, so whether it's a parallel flow or counter flow, it doesn't matter. When you have temperature fixed at the terminals, you already know the heat transfer. Okay, so the total heat transfer is known. So it doesn't matter whether you do parallel flow or counter flow, both will have same heat transfer. Then what do you guys think would be the difference between parallel flow and counter flow? Where do you see the difference between parallel flow and counter flow? So the answer to this problem is simple. So the temperatures are given. So whether you put in a parallel flow heat exchanger or a counter flow heat exchanger doesn't matter. The heat transfer is going to be same. Okay, so both the arrangements transfer the equal amount of heat. So that is no. Okay, I hope it's clear. But why we need a parallel flow and why we need a counter flow, right? So if you think about it, you guys are thinking too much. It's simple. You have when you have parallel flow, you can find from here. Let's say let's try to find out what is the difference. Let's find out what is delta T or LMTD. So LMTD for parallel flow is uh, so 190 minus 180 is delta T2 minus 310 minus 50. 310 minus 50 divided by natural log of 190 minus 180 divided by 310 minus 50. Okay, so this will be 10 minus 310 minus 50 is 260 divided by natural log of 10 by 260. This is coming out to be something like 76.73 degrees Celsius. Okay, so actually 260 plus 10 divided by 2 is 135 degrees Celsius. So you know if you just take the mean of these 10 and 260, it's going to be 135 degrees Celsius. However, you can see that the LMTD parallel is, I think, is less than that, 76 degrees Celsius. So that is something I wanted to show you with regards to the first question. Now, similarly, you can find LMTD of counterflow, which is going to be 190 minus 50 minus 310 minus 180 whole divided by natural log of 190 minus 50 divided by 310 minus 180. So this is, how much is this? 140 minus 130 divided by 140 by 130. So it's 10 by natural log of 14 by 13. So this is around 134.9 degrees Celsius. And now here also, as I said, let's say you take a mean of 140 and 130. So that is 135, which is close to 134.9. So in a counterflow, if you take a mean temperature, the error would be very less. But in a parallel flow, the error is around like 50 degrees Celsius. Okay, that is something else. So that's not what we are interested here. So now the heat transfer is same, but LMTD is different for these two. So for parallel flow, it's 76.73. For counterflow, it's 135 degrees Celsius. So what would be the implication of this? So we know Q to be UA into LMTD, right? So now, for example, let's take that overall heat transfer coefficient is same. Okay, overall heat transfer for both parallel and counterflow, because it depends upon the dynamics inside the kind of convective heat transfer coefficient, the conduction resistance, and the fouling resistance. Let's say all these things is going to remain same for these two heat exchanger. Then what this actually says is A for a parallel flow heat exchanger is nothing but Q divided by U times LMTD parallel, and A for counterflow heat exchanger is Q divided by U times LMTD counter. Okay, now since LMTD is very high for counterflow heat exchanger, the amount of area required for heat transfer is less for counterflow compared to parallel flow. Okay, so what does this mean is you will have a more compact heat exchanger if you have a counterflow. If you have parallel flow, you need to have very large area. So if you want to find a what do you call area ratio, you can find that too. So it's going to be simply 135 or 134.9 divided by 76.73. So it's like 1.75. Okay, area of parallel flow is 1.75 times the counterflow. Okay, so 75% more than the counterflow. So your parallel flow heat exchange is going to be very big. You should have very high heat transfer area in order to get the same heat transfer rate Q. Okay, but in counterflow you can have a compact heat exchanger. So that is what the difference that you will have. Well, it's just additional information. In general, if the temperatures are fixed, it doesn't matter whether it's a parallel flow or counter flow, mixed flow, doesn't matter. Whatever the heat exchanger is, the heat transfer rate we can simply find from one of the fluids temperature difference. Okay, so that is itself is enough to find out the heat transfer rate. And the difference between the different kinds of heat exchanger, the different kinds of operations of heat exchanger will result in a different heat exchanger area, and hence difference in temperature differences. Okay, so that is what I wanted to show you today. I hope this is also I hope this all the three questions are useful for you, and if you have any questions, please let me know.
Sir, in last question, mean temperature, how much, sir?
And the last question,
For parallel and counter, parallel 76 and the counter 134.
right?
We get mean temperature of how much, sir? Around,
Mm, this is the LMTD. So
yes,
I'm just giving you an idea. So for example, let's say you take a mean temperature based on just delta T1 and then delta T2 instead of finding
okay, sir.
LMTD, right? That will be something like so for this it is something like 135 degrees Celsius. For this also it's something like 135 degrees Celsius. So this is an
Very
but
low.
actually it's 76.
Okay, okay, sir.
So you should use LMTD instead of mean temperature. But in counterflow, you can make such an approximation if you don't want to find LMTD, because these two are practically close. Okay, is that what you are asking?
Yes, sir. Same, sir.
Okay, all right. I hope there are no questions. So, what I wanted to tell, Mustafa also joined. So, in this question you have, right? So, this fifth one, it's actually a trick question. You can look at it. So, why both A, B, and C, D is a wrong answer is, so the final statement says all the above is wrong, right? Which is also a wrong statement. One of the option is right.
Okay, sir. So accepted answer is D is also included, right?
Right, right. The
Okay, sir.
same goes with the other week's question also.
Yes, sir. Yes, sir.
I didn't notice it before. When you guys asked, I was also thinking like you, and when you view it in the first time, you will see it as, but
Mm.
after you give a lot of thought, you can find out actually it's a trick question. So
Yes,
please
sir.
be careful. Like these kinds of question might come in your exams too. Okay.
Okay,
So
sir.
all the above statements are same goes with the week 9. It is more clear in week 9 also. All the above statements are wrong, which
Nice.
is also a wrong statement. It's one
Yes,
of
sir.
the
Yes, sir.
statement is
We
right.
checked it and we opted the right answer, sir.
Okay, okay. Yeah, that's great. Yeah, these are I think kind of gate kind of questions, so
Sir.
to be really careful. All right. But the other one, the pressure one, I talked with professor.
Okay,
He
sir.
said pressure does vary linearly with x, and the pressure gradient is constant. So that I think is marked incorrectly, and that will be corrected soon. So don't worry about it.
Okay, sir.
So I will follow up it.
Okay, sir. Okay, sir. Thank you, sir.
Okay. Any other questions you have?
Sir, in examination, we'll have a problem like questions or
Yeah,
same statements.
you will have both. You will have both. So
Both.
initially you did had problem kind of questions, right?
Yes, sir.
Only after convection you are having less problem questions. But the questions that we discussed during the problem solving session, a similar kind of questions you will end up having. So especially in convection, they might ask like if I change the viscosity, how the Nusselt number changes. If I change thermal conductivity, how the Nusselt number changes. All those kinds of questions can also come. Similarly, the questions that we solved today, these kinds of question also will come. Okay, so both problem word questions also will be there, numerical questions also will be there. Okay.
Okay, okay, sir. The problem is live section and assignment
Hmm.
are more expecting now.
Yeah, yeah. So I mean, you will not expect the same question. So these questions are the I made the questions. Okay.
Hmm.
So but your end semester exam questions are already prepared by someone else. I don't even know them. Okay.
Hmm.
But these questions are typical questions that has been asked in the previous years also. In previous years assignments, from there only I took some questions. Some of the questions I took from book. Some of the questions I took from previous year assignments. So a similar kind of questions you can expect.
Last month, 8 week exam is ended.
Hmm.
They were asked 30 questions. Out of 50 questions, 30 from assignment.
Oh, very nice then. Good for you.
That's also we're expecting now.
Yeah, yeah, you can expect for sure. But I'm not sure about Professor Suman Chakraborty whether he will also do that. Uh,
Uh,
yeah,
Sir is
but
preparing questions.
come again.
Sir is preparing question.
Yeah, yeah. It has already been prepared. So before the start of week 1,
Hmm.
they prepare all the assignment problems and also the final
Even
exam
even
questions.
even though most of the courses are some weightage is given for assignment questions. Most
Correct.
probably.
Yeah, yeah. I, the weightage is given, I guess. It's 50-50, right? No?
Maybe assist. Yeah, our 8 week exam is ended before 2-3 weeks before. My friend's colleague is attended the exam. Out of 50 question, 30 from assignment.
Mm-hmm.
Same question, same option. Everything is same.
Okay.
Minimum 50 percentage we are safe now.
Yeah. I mean, I cannot be for sure because I didn't see the question paper.
Hmm.
So you can
Even even
expect.
even though there is a common scenario for this
Yeah,
any
yeah.
maybe.
You can
Uh,
expect.
for some course weightage is 50%, some course is 20%. Like this, any common rule? Maybe any common rule? Yeah,
There is no common rule actually.
common rule.
No common
Okay.
rule. So
Uh,
it's just the convenience of the instructor. If professor wants to give assignment problems in the final exam, he will
uh,
give. If he doesn't
mm,
want to give, if he wants to give some new problems, he will give. It's up to the professor. We
okay.
do not have any say in it.
Mm.
There is no guidelines as such.
Sir, last 8th and 9th week assignment, the score is not updated.
Yeah, so only one eighth will be remaining same. There is no change in eighth. So that's what me and Avinash also has discussed. So
8th.
All the above question, Mustafa.
all the above, see the all the above statement is see in this the
Sir,
you know
one choice is contradiction to another question choice now. Why this? How will correct the all the statements are not going to wrong? Not the statement all not going to true.
see
One is contradiction. One option is contradiction to another question. Another option.
no
Okay.
you think about it. See here
Hmm.
the fourth statement says all the above statements are wrong, right?
Hmm.
But that
Ah.
is not true. It is one of the statement is true, right?
Ah.
So which means fourth statement itself is wrong.
That's we telling.
Yeah, which means
They
that
were
is also one
asking.
of the
They were
option.
asking. The question is which are not which are wrong statement.
Right,
Can you
which
open? Can
see
you open the statement? This eighth assignment.
eighth assignment, okay. This one, right?
I can't see.
So this one, which fifth one, right? You can't see the
We can. No problem. I will open this here. No, I will open here.
why you are not able to see? Give me a minute.
It's
I was
visible
able
to
to
me,
see.
sir.
Maybe I am seeing mobile. Maybe.
Oh, okay.
For
Okay.
me, it's visible, sir.
Okay.
I will check. And I will check.
Yeah. See, the fifth question says which of the
One,
following is wrong, right?
1 minute, sir. 1 minute, sir.
Oh, yeah. Take your time.
ఒక్క నంబర్ జా పర్మిషన్ నంబర్ జటా 1 minute, sir. I will opening.
Yeah, sure.
Okay. Which of the following is true?
Which one is this?
No. Avinash. Okay. Which of the following is are wrong?
Wrong.
Right, wrong.
wrong. This asking now.
Hmm.
All of the above are not wrong.
Right.
Our answer should be why this D should not be comes in answer.
No, no. The,
All the above, sir. What the mean all the above?
all the above statements.
Hmm. One
So
is
which of the
contradiction.
following is wrong? They are
One
asking.
choice. Choice is contradiction to another choice.
No, no.
Okay.
No, you think about it. So
Ah,
the fourth option is telling all the above are wrong.
sir, there is no telling wrong or true now. All
No,
the above.
the question is about which of the following are wrong, right?
Ah,
When you say all the above, what do you mean by that?
all the above are wrong.
Right.
This
So, but in
this
this case, all the above is not wrong.
why this we can choose choice 8D.
We should choose. Accepted answer should
Sir,
choose
sir,
D.
all the above mean there is not clearly mentioned all the above is true or false.
No,
In
It is
option,
in week 9. It is mentioned that it is all the above are
yeah,
wrong.
yeah. In week
That
9,
is,
it's mentioned,
yes, sir.
but in week 5, you think about it. Which of the following is wrong? They are asking, and
mm,
one of the option is all the above. What
mm.
do you mean by that? All the above is wrong, right? So let's say all the above is the right answer. What do you mean by that?
all the
All the above is
actually
wrong is the right answer.
all the above is not wrong.
Yeah, all the above is not wrong. That's for you.
Mhm.
But for example, let's say A, B, C, all the three statements are wrong.
But
Okay.
the question is somewhat clarity problem. They have to mention all the above are true or false.
Uh, I mean,
That,
you
that is
can
confusing.
say that. You
Mm,
can say that, but question says which of the following is wrong, and if the one of the option is all the above, then you should
mm.
say you should consider it as a all the above statements are wrong. Okay, and if that is the case, then D is also an option for this question. So you should give D also as an option. Okay. But
This is
week 9 they have corrected it. They have added it. All the above statements are wrong. So don't.
why the problem is happened in it now.
Mm.
Actually, they were all the above were not mentioned true or false. Why this
See,
confusion?
this is a trick question. We can argue in all other ways. Okay, but there has we cannot. This has nothing to do with heat transfer.
Uh,
Okay, number one. So don't worry much about it.
no problem. Point 33 is lost problem. I have scored too much. Very good score.
But yeah,
I, I,
yeah.
I already scored.
Congratulations.
Mm.
But it's
I scored. I
but
scored
I
600.
understand. See, I understand. Only all the above is present. All the above is right. All the above is wrong. Which one is the? What should I take? So that is there. But since the question asks about wrong statements, you can safely assume that all the above. So D option could you can read it as all the above statements are wrong. Okay. So even in exam, if you see such kind of question, depending upon the question you can you know
Assume.
take you can assume that D option is all the above are wrong. So
Yeah,
if you
all the
put
above
all
is
the above
telling.
are right, okay, so for
Mm,
example, if they say
mm,
just all the above, and
mm,
if they assume that all the above are right, then
mm,
that doesn't make sense. Okay, if you think about it. So
mm,
your question says which of the following is wrong, and
mm,
your similarly they give an option to be all the above.
mm.
Okay. Now, if you
Uh,
assume that all the above is correct,
mm,
right? That it doesn't make sense, right? So because the question it says wrong, and unless until it is explicitly mentioned that all the above statements are correct, you cannot assume all the above to be all the above statements are correct. You
mm.
understand?
Okay, okay.
See, so what you can put instead of all the above? So that's your
Actually,
question, right? So you are telling that it's a
I have assumed why, but all the above statement are true. All the statement are
how
false.
So there are two options. Only two options you have. All the above
Mm.
statements are true.
One is contradiction to another. Now, why this I
See,
selected this
whatever
case?
the option you take, you can
Mm,
either take all the above statements are true, or you can take all the above statements are wrong. Both is going to tell that D option is wrong. right? You take all the above is true. Is the all the above is true? No, right? Two of the statements are wrong. So still D is a answer for this question.
Okay. That's correct.
That's correct, right? So whatever the thing you take, all the above are right or all the above are wrong, it is
Mm.
going to be wrong only.
Mm.
That
Yeah.
statement is going to be wrong for this question. So
Yeah.
you have to select that option, right?
Okay.
Okay. It's a trick question. So similar question, if it comes, you think a little bit before answering.
Okay.
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 All
No
right.
problem. That's actually confused. The sentence in question is confused.
Yeah. I also got confused when you guys first came to me. I also thought you guys are right. And
Mm.
today I was thinking, what is this? Why is this question wrong? How can they repeat the same mistake twice? And then I was thinking about it multiple times, and I
Then only.
wrote like a truth table whether this can be right or wrong. Then I was able to understand. Okay, this is what they are telling. Okay,
Mm.
so think a little bit before answering because it's a multiple choice questions. Even though we know the concepts, we might end up losing marks because of this. Okay,
Mm.
which is unfair, but there is no other option. This is only way we could conduct an exam. Okay,
Whether the score is updated.
the only one right week
Nine,
9 question 4,
fourth
the
question.
Means,
fresher, right?
week 9th is not corrected.
It will be corrected, sir. Sir.
Corrected?
Is
Abhinav?
it not
Not
corrected?
corrected.
Not corrected. Same score is showing now also.
Yeah, score is showing, but it will be corrected. This fourth one, right? The fluid
Yes,
pressure,
fourth one, sir.
Ah.
Same.
it will be corrected soon. So professor told that it is X does vary with P does vary with X. Okay.
Actually, it will be the updated
Yeah, it will be updated soon.
later before examination will be updated now. Okay. This
Mostly,
is the last
right.
live session.
No, there will be one more tomorrow. We will just revise. So I will go through this entire notes that I have here, and I will also share it with you guys tomorrow. Uh,
PDF.
yeah, I will share this after we go through this, and then last session
Okay.
we will not solve any problems,
Okay.
but we will just revise the
It is
contents.
better it is better if you get in the PDF document instead of video. If it's getting PDF, it will better.
I will do both. Don't worry about.
What about transcription? We are checked about transcription, but the problem is transcription is not correct.
Oh,
No,
really?
not correct product.
I see. Okay.
Actually, we checked 55 transition. It is showing a video of nine. It's a video is different from lecture number and video are different.
Okay.
We checked the video lecture transcript of lecture 55, getting
Mm-hmm.
video of 12th.
Okay.
Disorder.
Okay.
If any official transit is if it is there any, it will
I will.
better.
Yeah, if I find anything, I will share.
Mm.
Sure.
That site is not updated. Some video is getting, some is not getting. If
Mm-hmm.
some getting file also in mismatched with the videos.
Okay.
We got only 3 weeks is remaining now before examination.
Mm-hmm. When is your exam?
Third
Third May.
May.
Third May, sir.
3rd
Third
May.
May.
Okay. Sure.
3 4 weeks. Maybe 3 weeks.
Okay.
3 weeks.
But you
Actually,
you can you can watch the video, no? What is the problem?
watch video is too time consuming. I want to repeat again and again. Difficult now.
See, when you do it once, you should also take notes so
Actually, we are
that you
taking
no
note.
need so that you no need to view the lectures again.
Okay, we are prepared note. Even though
Mm-hmm.
if it is any confusion is there, it is difficult.
Okay, you if you want to go back and check, you
Go back and check. It will be difficult. Now, if it is transcript is there, we can read it before examination. We can repeat it within 10 minutes. One video, 1 hour section. We can go through within 10 to 15 minutes.
hmm. Okay.
That is that is beneficial.
So what
Hmm.
What are
difficulty we are
the
facing is
courses are,
for reference we have to go to that video and timestamp we have to go and check. That's
Hmm.
the difficulty we are facing. If it is transcript, we can just
actually
search
I
in
watched
PDF.
almost a video and not are making. All the notes making is not possible. So somewhat we getting somewhat what we not understanding. And
Right.
again watching is difficult. If it is any transcript is there, we are easy to go again and again.
Okay.
Time saving.
Hmm.
It is a coursework. This is why this I'm we are telling. This is not only a certificate course. We are selected NPTEL as a coursework of our PhD work now.
Okay. Okay.
Why this?
Hmm.
Some courses are having a transcript officially. They were
Hmm.
giving in NPTEL site, direct site. They were giving.
Right.
Before the video link, there is a transcript is automatically opening.
Correct. Correct.
They were taken the printout and marked the important points and repeating.
Hmm. So other option is you can refer books also. If you have any doubts, if you want to go back and check,
Hmm.
you can take the this Incropera book,
That's
e-transfer.
okay. That's
That also
a,
you can do.
syllabus is too wide now. Transfer. Why this now? Syllabus is too wide. Watching the lectures, most of questions are coming from these lectures.
Yeah. So
No
in
problem, no problem. If it is
hmm,
available, please.
yeah, sure.
We don't know if it is available or not.
Hmm.
If you any
If I come across, I
data,
will share. Yeah.
Yes, sir.
uh,
Yes, sir.
If I come
if you
across, I
discuss
will share.
with other NPTEL faculties, if any sir in with sir transcripts is there,
Hmm.
please. How if it is there, how will get only share through NPTEL?
If I get anything, I will post it in the common forum. I
Mm.
guess you guys must have subscribed to it, so
Mm.
you should be getting the
Well,
email.
please try maximum. If it is a time consuming after 3 weeks, again
Hmm.
we watching video again no time now.
Right, right, right. Sure.
Assignment question almost we studied
Hmm.
thoroughly. The problem
Hmm.
it is not too much problem questions, too much doubts. We are clarified almost 120 questions. Is gone through now.
Right, right. Yeah.
Mm.
Sure. I will check
I
once.
got I got 106 numbers.
What do you mean by that? 106?
600 I got in assignment.
Oh, wonderful.
Six,
Congratulations.
six assignment and 289
I see. So assignment is like 50%, right? For final grade calculation.
and 25%.
25 marks, sir.
25 percentage is assignment.
25 for assignment
Hmm.
and 75 for end semester.
Oh, okay, okay, okay.
Out of 75, we have to minimum 30. Out of 75, we have to make 40%. 30 mark we have to get.
Okay,
30
okay.
mark.
Okay, okay,
And
okay.
for assignment, we need only 10 mark.
Mm-hmm.
But our criteria is different. For our
Okay,
PhD,
in NIT, okay.
NIT, we had to get minimum C grade. C grade mean 64 to 54 mark.
Okay, okay, okay.
If it is getting just a pass mark in NPTEL,
Mm-hmm.
30 mark, and in assignment 22, total 52, we will fail.
Okay, okay, okay.
We have to get minimum 54.
And what if you get 90 or above?
90?
If you get a total 90 or above, will you be given a higher
Yes,
grade?
yes, grade, yes, grade. Our
Right.
criteria is, I will give, our criteria is, um, 1 minute. Avinash, you have in the NPTEL grade is,
I'll search it now.
uh,
So you have like S, A,
Yes,
B,
sir. Yes,
yeah.
sir.
C. Okay, 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 okay. That's fine. That's fine.
Actually,
Hmm.
for NPTEL,
Hmm.
uh, we have to maintain minimum C grade, unless otherwise I have to repeat.
Okay, okay, okay.
54 to 60 C grade,
Hmm. Hmm.
61 to 67 B grade,
Hmm. Hmm.
68 to 79 A grade,
Okay.
80 up to 100 S grade.
Okay. If you get above 80, you will get an S grade.
Yes, great.
Okay, that's great.
This is the NPTEL. Other courses are different. For NPTEL
Mm-hmm.
only, this is S grade 80. For other course, 90 is S grade.
I see. Okay, okay, okay.
Okay, tomorrow last section now. Live
Yeah, yeah,
section.
yeah. Tomorrow we will be having one session. We'll
After,
be revising.
after, is there any doubt regarding any we can mail now?
Yeah, yeah. If you have any doubts, you email me.
Hmm.
I will be able to reply as soon as possible.
Okay,
Okay.
okay, okay.
Minimum like within a day or so, or give me like a day, I will be able to reply.
Okay, okay, okay.
Okay.
Okay, okay.
Okay, sir.
Free try
Or
maximum for free try maximum for transcript.
yeah, yeah. I will ask professor. I will
Okay, okay, okay.
email him.
Thank you.
I will ask professor.
Thank you, sir.
Okay. All right. Thank you. Thank you, Mustafa. Thank you, Avinash, for
Thank you.
joining.
Thank you, sir.
We'll meet tomorrow then.